And I am here to present a research project we did, which was actually funded primarily by the corn and soybean growers. And what we did is we used LiDAR data to assess how much erosion was actually coming from the riverbanks. So this is kind of a figure that's been presented many times, and it's one of the reasons we're all here trying to understand where the sediment sources are coming from. This is actually work done by Dr. Dan Engstrom. And what they found by taking sediment cores from the bottom of Lake Pepin is that in recent years, the rate of sediment filling there has increased quite drastically. So then additional research went on to identify what major river basins those sediments were coming from. And what they found is that 3/4 of the sediment, or as much as 3/4 of the sediment, was coming from the Minnesota River Basin, while it was only producing about 1/4 of the flow. And within the Minnesota River Basin, and I have it highlighted here at the bottom, is the Greater Blue Earth River Basin. So that's the area just south of us here in Mankato. Mankato will be right here where the Minnesota River switches direction. Within the Minnesota River Basin is the Greater Blue Earth River Basin, and that's going to be the area I'm focusing on here today for my talk. And the Greater Blue Earth River Basin produces 55% of the sediment that's found in the Minnesota River. So a large portion of that sediment going to Lake Pepin is actually coming from the Greater Blue Earth River Basin. And it also produces about half the flow. Now this is kind of a unique area in Minnesota, and it's actually really, really flat for the most part. 54% of the land has less than 2% slope. 93% of the land has less than 6% slope. And within the Minnesota River Basin, there was 3 general areas that had been identified as potential sources of sediment. There were fields, banks and bluffs, and ravines and gullies. And Giles, in his introduction, mentioned about these swales where you can see a little bit of sediment erosion occurring where it's getting a little lighter on top. However, in the Greater Blue Earth River Basin, it's really a pretty flat area. And although a few of those areas occur, for the most part, the fields are really flat. So there isn't really that potential in this area where 55% of the sediments in the Minnesota River are coming from. However, unique to these rivers are these extremely massive banks and bluffs that occur right along the rivers. And just looking at these, you can see there's a lot of evidence, visual evidence, that they're actively eroding. There's no vegetation on the side of them, and they're completely exposed. For a little bit of scale here, a picture really doesn't do it justice, but to give you scale, this is actually Satish Gupta standing right below the bank here. So it gives you a little bit of an idea how big these bluffs can get. And here's another view of one of the bluffs, and this is on the LeSueur River, just southeast of Mankato. And this is right next to a little subdevelopment of houses. And this unfortunate property owner has a tool shed right here that's just a couple years away from going into the drink. And we haven't been out there recently, so this could be gone already. This was taken in 2009 from an aircraft with a side viewing photograph. And what you can see on this bank is that there is a number of trees sitting right in the middle of the bank. And we know from viewing this bank that this has been void. Whoop. Well, how did I do that? How do I get that started? I think I hit the wrong button there. All right. Well, this bank for a number of years was void of trees, but now you see all these trees sitting in the middle of the bank. And the reason for that is they came off the top of the bluff and fell right on top of it. And all this material eventually goes down into the river and gets pushed downstream, and most of it, or a portion of it, will make it to Lake Pepin. So there's another way we can kind of look at this to get an idea of what's happening with these rivers. And what we can do is we can go back into the historic air photos and see where the river was in the past versus where it is today. And what I actually did is I took this into our computer software back in the office, and I digitized the path of the river in 1938. We can then take that path and overlay it on top of a current image in 2009. And as you can see, there's been some pretty drastic shifts in where this river is. And this bank is 100 feet tall, actually. And I'm going to be coming back to this bank a little later in the presentation with an example calculation. But since 1938, this river path has moved 230 feet into this 100-foot tall bank. So if you kind of start to think about that, that's a lot of material. And another thing, I'm going to flip back here. This bank in 1938 was heavily vegetated. That's all trees along there. So in some of the traditional systems, what they'll recommend is that you put vegetation into the side of a riverbank to help stabilize it. But from our observations that we've been making in these historic air photos and out in the field, that really doesn't take care of the system, or that doesn't really have the ability to stabilize it in a lot of instances. So this isn't the first project to try to identify where the sediment sources come from. I think I'm sure a lot of you have seen a number of different projects coming out trying to identify where the sources of sediment are coming from. It's kind of been an interesting trend. I have this table orientated so that the older studies are at the top, and as you move towards the bottom of the table, the newer studies are at the bottom. And what you see in this general trend is that the further along we've gotten into the research, the more and more people are starting to acknowledge that riverbanks and bluffs are the primary source of sediment. So there's becoming an agreement in the scientific community that the majority of sediment is coming from riverbanks and bluffs. And now just to mention, this isn't a comprehensive list of all the projects. There's other ones. I just put a kind of a representative sample up there. Now, one of those projects did use the technology I'm presenting here today, and that was a project by Toma and others in 2005. And they actually took an airborne LiDAR system and mounted it to the belly of a helicopter and flew a 35-mile portion of the Blue Earth River. And from that 35-mile portion of the Blue Earth River, they found that 23 to 56% of the sediments were coming just from the banks in that 35-mile portion. So this was kind of the pilot project to what I'm presenting today. And we set out with the objectives to kind of broaden the scope of that study. Now, what exactly is airborne LiDAR? What you do is you take a LiDAR data system and mount it to the belly of an aircraft. That aircraft then passes over the landscape, all the while shooting down thousands of laser pulses every second down to the landscape. For each laser pulse that gets sent down, the LiDAR system records the travel time it takes for that laser pulse to go down to the ground and return to the aircraft. Between that travel time and an onboard GPS unit, the aircraft and the LiDAR system are able to determine what the elevation of the Earth's surface is. So here's just a little visual representation of what the LiDAR data looks like when we get it back into the office. And this is a bluff on the Le Sueur River, and we've actually been out to visit this one, and this is probably one of the biggest bluffs we've been able to go out and see. And this is a 2005 LiDAR data set that we had, and this is a 3D representation of just the LiDAR data. And here's the 2009 LiDAR data set. And it's a little hard to make out, but you can see a little bit here in the top left corner is that you're starting to see some slumps, and you can see the evidence of that when we put an air photo on top of that 3D representation. You can see areas on the banks where material is starting to move down the surface of the bank. And just to give a little bit of perspective of how large this thing is, I did some measurements in the office of how tall the bank is. This thing is actually from the surface of the water up to where the top of the bank is 200 feet tall. And the top of the bank sits back from the river 300 feet. So it's a pretty big, large bank. If you do a little bit of geometry, you can find out that if you were just to go down the surface of the bank, that's over a football field long, 360 feet. And the entire bank surface has an average slope of 92% or 40 degrees. So not only are these things really large, they're really steep too. So what we set out to do with our LiDAR data is, at first, is to just quantify how much sediment is coming from the banks and being contributed to the rivers in Blue Earth County, Minnesota. We also did a little soils data analysis so that we could calculate how much phosphorus attached to the soil material going into the rivers was coming from the banks. And then just to make sure that the LiDAR data we were using was an appropriate tool for these calculations, we did an uncertainty analysis and an accuracy assessment. And then a number of the projects that have already been conducted in the state look to separate out tall bluffs from shorter riverbanks. The tall bluffs in the greater Blue Earth River Basin are a pretty unique feature. There aren't too many places in the state where there's bluffs that get up to 300 or 200 feet high. So what we did is we separated out in an analysis any area that had less than 10 feet of relief we called a small bank, and any area with greater than 10 feet of relief we considered a tall bluff. And I'll be presenting that at the end here. So our study area was just within Blue Earth County. So the river miles just in Blue Earth County. And we analyzed the Watonwan, Perch Creek, Blue Earth, Maple, Big Cobb, Little Cobb, and Le Sueur rivers. And we also, for one of our analyses, picked up the section of the Minnesota River that runs along the northern boundary of Blue Earth County. And now just kind of a note at this point, because our data was only for Blue Earth County, we're unable to assess with the data sets we have what's going on in the river lengths beyond the county. So all the results I present here today are kind of a conservative estimate because whatever erosion is occurring within the county, there could be additional erosion occurring in the river miles outside of the county. So as I've mentioned, we had a 2005 LIDAR data set, and Blue Earth County had already collected that, and they provided us with that data set. We then commissioned our own data set in 2009 for the entire county. We also took a number of soil data samples so that we could analyze the data for soil texture, bulk density, total phosphorus content, and soluble phosphorus content. Then we also got some water gauge data so that once we made our net volume change calculations and our mass wasting calculations, we could compare what was coming from the riverbanks to the data that was collected at the water gauges. So we could get an estimate of what percent the riverbanks were actually contributing at the water gauge. So this slide is a little bit wordy, but it kind of steps through the process of making these calculations. The first step is to identify where the riverbank zones actually are. And what we did is we used our LIDAR data set to identify where the top of the bank is. We then took the LIDAR data set and identified the bottom of the riverbank using the high water mark. Now the reason we have to do that is because the LIDAR data system we used does not have the ability to penetrate the water surface. So anything below the water surface we were not able to account for in this analysis. We have to just take the bottom of the bank at the high water mark to the top of the bank. Then using those zones and the difference between the 2009 and 2005 LIDAR data set, we can make a net elevation change calculation for the riverbank zones. We can then take that net elevation change and multiply it by our area to get a net volume loss from the riverbanks. Then using the data from our soils analysis, we can calculate that net volume times the average bulk density of the soil to arrive at a mass wasting calculation, or the weight of material that left the riverbanks. Then, multiplying that weight times the fine content of the soil from our soils data analysis, we can arrive at the percent fine sediment contribution from riverbanks to the rivers. And the assumption we make at this point is that all the silt and clay is moved downriver, while the percentage of the material that is sand stays in the river basin or settles out somewhere. So just to make this a little clear, I know that slide was a little wordy and the technique might not be all that clear at this point. I'm going to walk through a sample calculation using the LIDAR data. And this is a bank we've visited several times. This is on the Blue Earth River about, I think it's 10 or 15 miles south of Mankato. And the property owner's been nice enough to let us walk out to this bank several times. And this is actually a photograph that we took just this spring. And we're standing on the right point of this bank, looking back across the bank like this. And as you can see, just looking at it, there's a lot of evidence of erosion going on here. You can see no vegetation present. And you can also see material starting to fan out at the bottom that has come off the top of the bank. Then what we can do is we bring our LIDAR data into GIS and we subtract the 2009 from the 2005 LIDAR data set, and we can start to get some elevation change calculations. And what you see for this riverbank represented in the red areas is that there's areas with as much as 28 feet of elevation loss between 2005 and 2009. So that's just the straight vertical loss. That's not getting into the volume yet, but just straight vertical loss of up to 28 feet in these red areas. Then the blue areas at the bottom show where sediment has accumulated, so up to 10 feet of just sediment accumulation from the erosion at the top of the bank. Then we can summarize for the entire bank how much volume has left that area. And what we find for this bank, just this bank, is 4,114 cubic yards of volume loss every year during our study period. Then when we take the bulk density from our soils analysis, we can multiply that out, and we get 5,928 tons of material leaving this one bank every year of our study period, for each year during our study period. Then, taking this number multiplied by the percent silt and clay content, we find that 3,486 tons of material left this bank every year and went down the river. So just from one bank, you kind of get the sense that it's a pretty impressive amount of material that's eroding off of these and going into the river. Now there's a couple of caveats for LIDAR data here. Generally when it's delivered, it comes with about a plus or minus 1 meter horizontal accuracy and a plus or minus 15 centimeters or about 6-inch vertical accuracy. And there's a number of factors that can impact how this accuracy varies. And the one that's really important to this project is terrain slope. The reason for that is all of our calculations are occurring on areas with a pretty significant amount of slope. And that lower horizontal position could potentially impact some of the accuracy of the LiDAR data calculations. And I've come up with this little cartoon to kind of demonstrate what I mean by that. So if you have a 3-foot shift, so plus or minus about a meter, about 3 feet, shift in horizontal accuracy on a flat surface, you're not really going to see much of a change in elevation more than likely. However, on these steep surfaces, that same shift could potentially create a large shift in the accuracy of the vertical measurement. So what we did to account for that is we actually ran a number of secondary accuracy assessments on our data. The first thing we did, after we generated our bare earth elevation models, so our elevation models for the entire surface of the county, we took 78 hard surface points measured by the Minnesota Department of Transportation in 2005 with GPS units in the field, and compared the elevations they measured to what we calculated with our 2005 and 2009 LiDAR data. We also then took 124 points in areas across the county that we knew had steep terrain and no elevation change between 2005 and 2009. We then went forward with the assumption that we should see 0 change in elevation in our LiDAR subtraction for those areas. And any change in elevation we'd assess as an error in the data set and summarize in our results. And then we did one more assessment to see if the vertical slope, the change in slope, was impacting our calculations. And that's an uncertainty analysis using minimum level of detection thresholds. And this is one of the most commonly applied techniques for assessing uncertainty in calculations done with digital elevation models. And what you do is at each threshold you set, you take the data beneath that threshold and drop it out, and then recalculate your result to see if dropping out that data had any impact on your net volume change calculation. So at the 0.25 feet mark, what I do is at plus or minus 2.5 feet, anything below that threshold would be dropped out of the analysis, and then we recalculate our final result to see if we're having a significant impact on what that value would be. So if you have a significant impact from just dropping out a small threshold, you kind of get the idea that your data, most of your data might be falling within a threshold where you don't have that high a degree of certainty of what your calculation would be. So we assess that just to make sure that we could have a relatively high degree of certainty or potentially uncertainty in our calculations. I have a little figure put together for this too, just to make the explanation a little clearer. So this is another bank on the Blue Earth River. This one is actually just adjacent to Vernon Center. This is about the property line of Vernon Center right here, and this is actually a property owner's little grassy area, and they have a garden right behind this bank. And on this bank from 2005 to 2009, our LiDAR data is indicating as much as 32 feet in elevation loss in some portions of the bank. So then at each threshold, starting at 0, here's the calculation with no data dropped out. And here's a threshold with 1.5 feet. So any elevation change between plus or minus 1.5 feet has been dropped out of this calculation. And as you can see, even at that level, you're not having a really large change in the net calculation. But once you start to get out at a little higher thresholds, then you're starting to see a drop in the pretty good change in the calculation. And once again, this is just for this one bank. So getting into some of the results. The accuracy assessment turned out pretty good. Our accuracies came in about plus or minus 8 inches for the 2005 LiDAR data set, plus or minus 6 inches for the 2009 data set, and plus or minus 7 inches for our steep terrain analysis. And this is all pretty close to the kind of the standard accuracy that's delivered by the data vendors. And this is a histogram of our steep terrain accuracy. So what you're seeing represented on the bottom here is our change in elevation calculation and the frequency at which those 124 points occurred at different changes in elevation. And the good thing here is this is it's normally distributed, meaning that it arcs kind of like this, and it's centered around the 0 mark. So a good bulk of our error, or the changes in elevation, were measured properly at around the 0 mark. Now the results of our LiDAR uncertainty analysis are summarized in this figure. And these are the different thresholds I applied and presented earlier at different levels. And this is our net volume change calculation. So at the 0 mark, the net volume change was about 1.8 million cubic yards of material lost on the rivers in Blue Earth County. I got another slide coming up where I include the Minnesota River. This number does not include the Minnesota River. And what you see here, and it looks a little counterintuitive at first, is as we proceed through these thresholds, our net volume change calculation is going up. You might start to think about to yourself, well, how does the cubic volume lost go up as they're dropping out data? Well, this actually, when you analyze it, is performing just how we'd want it to, because a lot of the deposition that occurs is at finer elevation. So when you start dropping out these threshold levels, most of what you're dropping out at first is the deposition. So that we're actually seeing exactly what we'd hope to, is that as we drop out the lower levels, lower changes in elevations are dropping out, so we're removing deposition from the calculations. And once we get to the higher levels, these greater changes in elevation, at least how we interpreted it, would have been the mass failures on the riverbank. So once you start to get to these higher threshold levels, you're dropping out erosion observations, and your net calculation starts to come down a little bit. Here's another little way of looking at the data. So what we have here is different bracketed ranges for the change in elevation along the riverbanks. And then this is the percent makeup of our total volume calculation for each of these zones. And what you see is that by far the bulk of our data came from calculations where there was a loss of elevation greater than 1 feet. So what this indicates is that most of our measurements and most of our net volume change is made up of areas where there's a pretty large change or loss in elevation on those riverbanks. So here's our actually net volume change result summarized by river. And if you sum these all up, this is 2.24 million cubic yards of volume loss between 2005 and 2009 for the river miles we analyzed within Blue Earth County. This can be a little deceptive. The Blue Earth River, although it did produce the most sediment among these rivers during our study period, the Blue Earth River is much higher than the rest. However, we analyzed the most river miles of the Blue Earth River. So this kind of gives you the indication that as you analyze more river miles of these rivers, you're going to get higher and higher sediment loads coming from the riverbanks. So if we were at some point able to extend this analysis beyond the border of the county, it's very possible that some of the numbers for these other rivers would jump out as we analyze the entire extent of those rivers. So here's a figure showing where we separated out the different contribution from bluffs versus banks. So the blue bars are showing those areas with greater than 10 feet in relief, and the gray bars are showing those areas with less than 10 feet in the relief. And this can be a little misleading too, but if you remember back to the previous slide where I was showing the net volume change, the rivers, the Blue Earth River and the Sewer River, which were responsible for most of that net volume change, have most of their sediments coming from bluffs, or over 80%. So what we can then do is switch this so we summarize it for all rivers. And when you do that, you see that 75% of the volume loss for these rivers in Blue Earth County is coming from the really tall bluffs. And interestingly enough, these tall bluffs only occupied about 33% of the river miles that we analyzed. However, if you take account for their surface area and compare the surface area of the bluffs to the surface area of the banks, the surface area of the bluffs occupied 63% of the area we analyzed. So you have these bluffs that are somewhat spread out, occupying only a small percentage of the river miles that we analyzed, but they have these massive surface areas that are contributing to the sediment in the rivers. So and there's some other applications for this data too. Not only can we do these wide-scale analyses, we can pick out singular banks that we want to look at to see how much they're contributing to riverbank or to sediments in rivers as well. And this is the bluff that I showed earlier in the presentation that was 200 feet tall. And what I did is I came back to this bluff and I did just a calculation of erosion for this bluff, similar to the example I presented. And what we find on this bluff is that there's areas with as much as 40 feet in elevation loss. And now the picture here really doesn't do it justice, because this thing is a football field in length, more than a football field in length going down it. So when you see just these couple of little red patches, it doesn't really look like it's going to amount to much erosion. But when you run the numbers, this one bank on the LeSueur River actually lost 22,571 cubic yards of material from 2005 to 2009 based on our LiDAR data calculations. And when you start converting that into a weight, that's 32,532 tons. or 19,129 tons of sediments pushed downriver. And if you put that in the context of our entire analysis, this one bluff was responsible for 7% of the volume change for all the river miles we analyzed on the Lusua River. So another thing you can do, and after I did that analysis, I got to thinking, well, if this one's eroding so much, there must be just maybe there's a select few that are producing most of the volume change in the river. So what I did is I went back into the data and I just pulled out the 10 most erosive bluffs for the river system. And if you're counting back there, the erosive bluffs are highlighted in red here, and if you're counting, it only looks like 9. That's because I had to exaggerate the colors a little bit to make these things jump out. And this big red blob up here is actually 2 bluffs. But if you look at the volume loss from these 10 bluffs, just these 10 bluffs made up 27% of our net volume change calculation for the Lusua River. And you can start to scale up a little bit and look at this thing in sections. So what I did is I divided the river into sections based on where gauges are located on just the Lusua River. So the red area, the Blue Earth confluence, as I've labeled it here, goes from a gauge just before the Blue Earth confluence with the Lusua River to a gauge at County Road 8 straight south of Mankato. The green section then goes from the County Road 8 gauge to a gauge at St. Clair, or the green section, excuse me, and the blue section goes from the gauge at St. Clair down to the county boundary. Now the Lusua River does extend beyond this. You can see the little blue line, but this gives you an idea of the area that we analyzed for the study. And when you break it down, the center section is producing by far the most volume loss out of the river sections. However, it's also the longest section we analyzed. So if you look at this as a volume loss per unit mile, you see that as you move from the start of the river downriver, the bulk of the volume loss as a per unit mile measurement is occurring in the front section, and it decreases as you move downstream. Now getting back to the larger scale calculations, this is actually the percent contribution estimate of river banks to the different gauges. And I have this broken out into 2 different sections here, because what we did is we summarized the sediment contribution to sediments in rivers from riverbanks based on different gauges. So these 3 rivers, the Blue Earth River, the Watonwan River, and Perch Creek, were summarized based on a gauge below Rapidan Dam before the confluence of the Blue Earth River and the Lusua River. And the Lusua River, Maple River, and Big Cobb and Little Cobb rivers were compared to the gauge on the Lusua River right before its confluence with the Blue Earth. So 62% of the sediment we estimated at the mouth of the Blue Earth River below Rapidan Dam were coming from river banks and bluffs within those rivers. And 78% of the sediment for the Lusua River gauge was coming from bluffs and banks along the Lusua River watershed in the Maple, Big Cobb, and Little Cobb rivers. And now if you go back to our soil data analysis, we can take what we found for total phosphorus content in those soil data chunks that we analyzed and determine how much of the total phosphorus in the rivers was coming just from the sediment falling into the river from the banks. And what we found for the total phosphorus measurement was that 42% of the measurement at the gauge for total phosphorus was coming from the banks and bluffs on the Blue Earth River system. And 46% of the total phosphorus at the mouth of the Lusua River was coming from the Lusua, Maple, Big Cobb, and Little Cobb rivers. And we can do the same thing for soluble P. And this is quite a bit smaller number, about 0.17% at the mouth of the Blue Earth and 0.15% at the mouth of the Lusua. And that's because most of the phosphorus in the bank materials is tied up as total phosphorus rather than soluble phosphorus. Now, kind of a little caveat here. Sampling these banks to do the soil data analysis can be quite difficult. As I showed you with that big bank at the start, it's got about a 90% slope. It's actively eroding, and it's 200 feet high. So although I'm kind of new to the university, I wasn't too quick to volunteer to shimmy down the side of it to gather soil samples. So what we did as an alternative to give a kind of a bracketed range for our calculations is we went back into the literature and pulled out other values other researchers had used to kind of provide a minimum and maximum for our calculations. And the data sources we used was one from Karen Graham. She's a researcher at the University of Minnesota Duluth who does some work in this area. And she had over 300 soil samples to come up with her 65% silt clay estimate. Then we also took, I think it was 5 soil cores from the Minnesota Geological Survey that are stored up in Hibbing, and took their estimates of percent silt clay for those 5 different soil cores. We then applied this information in combination with ours to come up with a bracketed range. And the percent sediment is shown over here, but just to kind of summarize it, make it a little more clear, for the Blue Earth River, using the bracketed values, anywhere from 49 to 73% of the sediments at the gauge were coming from the riverbanks. For the Le Sueur River, it was anywhere from 61 up to 92% on the high end. So, and if you compare our data values, which are right here in the corner, to the bracketed range, we kind of came out somewhere right in the middle. So we're pretty encouraged by our results on that. So some conclusions for this section of the presentation. 1, bank erosion is by far the primary source of sediment contribution to rivers in the greater Blue Earth River Basin, with as much as 2.24 million cubic yards of volume loss from the riverbanks and bluffs. Some 62% on the Blue Earth River and 78% of those sediments on the Le Sueur River come from the banks and bluffs. And if you take the high end of the bracketed range, this can stretch up to as much as 73% or 92% of the material, the sediments floating down the river coming from riverbanks and bluffs. And as I've mentioned a couple times, these estimates are possibly conservative because we are only able to analyze the river miles within the county. So there's river miles outside of the county that could be eroding that we were not able to analyze in this study. Then also, bluffs by far contribute the most of the sediment, with 75% of the materials coming from the bluffs, while only occupying 33% of the total length of the river channels. So they're occupying a small space on the river by river mile length, but they're contributing most of the sediment. And then kind of the final point is that multi-temporal LiDAR served to be a pretty useful tool in this study for quantifying how much riverbank erosion was coming down the river. So some of the future work we could move into is expand the area investigated with multi-temporal LiDAR. As you saw throughout this presentation, I only really showed data on the Minnesota River once, and that's because we only had a small section. The state has now collected an initial LiDAR data set for the entire Minnesota River Basin. So there's an opportunity to come back and analyze different portions of the Minnesota River Basin. And in addition, another opportunity would be to come back and take another LiDAR data scan in the future where we analyze not only the river miles within Blue Earth County, but outside of Blue Earth County. So we can actually get the full extent of erosion from the entire length of the river. And if you did take those opportunities to come back and continue to do LiDAR data scans in the future, you could also start to compare these fairly accurate measurements with changes in precipitation and start to get a handle on how climate has impacted the rates of erosion from these bluffs and banks. And another kind of unsolved mystery, and we've talked about this a lot, Satish and I, is the mechanisms that cause bank erosion. I think he's going to be talking a little bit more about that in his presentation, so I'm kind of just going to leave it at that. But there hasn't really been a focused project that has quantified what mechanisms are the primary reason for the erosion to occur. And then finally, I alluded to this a little bit, but future work could also characterize the impacts that climate have on the amount of riverbank erosion. And I was initially going to end it here, but I finished an analysis from a new project we've started just this last Monday. So I plugged in a little bit more information at the end here. And we're actually taking on a project now where we're going back in time using historic air photos and trying to track how much riverbank erosion has occurred during different time periods. Kind of the reason for this is in recent years, the probability of having larger amounts of precipitation has increased quite a bit. And I only have this one figure on this because I believe Mark Seeley, who's going to be presenting a little later in the afternoon, will probably go into more depth about changes in climate. But that change in precipitation, the increased probability that for higher levels of precipitation, makes you start to wonder how does precipitation impact rates of bank erosion? So what we're doing for one of the objectives of the study is to actually try to quantify what's occurring, what the relationship is between climate and riverbank erosion. And what we're doing is we're using our LiDAR data as a base layer. We're getting climate data records of precipitation stretching back to 1938, and then we're taking historic air photos that stretch back to 1938 to estimate how much volume is being lost from these riverbanks during different periods. And here's the years of data that we've been able to find for Blue Earth County. So at each of these periods, we go back and try to identify where the position of the top of the bank was. So here's a little example, and this is a 1938 air photo, and this is one of the riverbanks we were able to identify. And one of the hard parts of using historic air photos is if the top of the riverbank is heavily vegetated, you can't identify where it is. So we're limited in this analysis in a little bit to just collecting kind of a sample of eroding banks based on where we can identify where the top position of the bank is. Then using this historic position of the bank and the present day position of the bank identified with our LiDAR data, we calculate how much volume loss had occurred between the two time frames. And we use just a couple of simple little equations multiplying the height of the bank by the distance the top of the bank has eroded to arrive at a volume loss. And then based on the length of the bank at the front of the river and the amount of area that's been lost, we can also calculate the rate at which the top of the bank is receding. And kind of the two assumptions we have to make here is that the bank height has remained consistent throughout time, because all we have as a base data layer to calculate that height is our LiDAR data set, and that the slope of that bank has remained constant throughout time. So the face of the bank has looked the same, and the height of the face of the bank has looked the same since 1938. And for the Blue Earth River, I finished this analysis just for the Blue Earth River. This is showing the number of observations of bank recession that I was able to track at different periods. So for 1950 to 1958, there was 29 different banks that I was able to identify in the historic air photos and then calculate between the two different periods. In total, there was 97 unique banks that I found in the Blue Earth River that I was able to identify with the historic air photos. And here's one of the preliminary figures we've come up with. And what this is showing is the average volume loss by period per unit area. So per unit area of exposed surface, how much volume was coming off of those riverbanks. And it's on top of the total precipitation for those periods. And those of you who keep track of the rain might be looking at this and saying, well, that's a lot of rain, how did he come up with that? But some of these are from large spans of periods. So some of the periods I showed here are from 1971 to 2009. And what we did is we actually just we added all the annual precipitation that had occurred through those periods. So you come up with some pretty high numbers. You then compare that total precipitation to the average volume loss per unit area. And when you do that, initially, this is a preliminary result, and we still have more work to do with this. Initially, it does look like volume loss per unit area corresponds quite nicely to how much precipitation is occurring within the Blue Earth River Basin. And the precipitation we got, I didn't mention this, was just for the Blue Earth River Basin. It was summarized for us by the University of Minnesota Climate Office. So you can kind of, just preliminary, because we still have more work to do on this, start to draw the conclusion that bank erosion rates are increasing with the amount of increasing precipitation. So this is kind of starting to tease out how climate is impacting rates of bank erosion. And so what we have left to do on that study is finish the rest of the rivers for Blue Earth County for the same analysis I just presented. And then we're going to actually take a look at how river widths and sinuosity of the river have changed over time in relation to precipitation. So kind of the take-home points from this whole thing are banks and bluffs are the primary source of sediment in the greater Blue Earth River Basin, with the bluffs contributing the majority of the sediment. Airborne LiDAR serves as a good tool for quantifying riverbank erosion in the greater Blue Earth River Basin. And some preliminary results from the study we're just starting to undertake indicate that bank erosion rates are varying directly with precipitation. So here's some acknowledgements. I'd like to thank my co-authors, Blue Earth County, for providing us with the data set. Scott Salisbury, who's works with Blue Earth County, and he's helped us out at the start of this project and throughout the project, coordinating some of the things we've done. Minnesota Corn and Soybean Research and Promotional Council for funding the project. Scott Matheson, formerly of the University of Minnesota Mankato, or Mankato State University, but now he's worked with the Department of Ag. He helped us out with getting the water gauge data. And Alan, I'm going to mispronounce his name, Knabel, and Gary Meyer, who were with the Minnesota Geological Survey and provided us with the soil core data. So with that, if there's a little time for questions, I want to show this real quick before we take the questions. This is a pretty unique feature that was out on the Blue Earth River. This is in June of 2010. We came back later in the year, and it was gone. So with that, I'll take any questions if anyone has any.
Time for a question. There's one back here. Gary?
I assume that the organic matter in the bank's sloughing. Have you ever checked the organic matter? I'm guessing it's low, but have you done an actual measurement?
No, we have not for this study, and that would be something interesting to do because there is some there are differences between what the organic suspended sediments do downriver versus the inorganic suspended sediments, and that would be an interesting number to come up with, but it's not an analysis that we've run.
There's another one back there.
My question will pertain to blacktop, cements, whatever you have. I wish someone would do a study on the amount of additional things we've done, and I'm going to use the city of New Ulm today. It has covers 3,500 acres and has 41 miles of storm sewer.
I'm not sure on the question there.
Probably more of a statement that we should be looking at. I think he's making that suggestion. We should be looking at it, and not necessarily the question.
All right.
One more question.
Les?
Les.
Most of what the photos you showed the primary bank and bluff erosion being on the outside bends of the river.
Correct.
Which would say something to mechanisms. So is that observation true? Did you see that throughout the system?
The question is that most of the photos I showed through the presentation demonstrated, or at least depicted, that the erosion was occurring on the outside meander of the river. And yes, and what we've observed in the field anyway, and I think Satish is going to talk about this a little bit more, is that as the river starts to cut into the bank, seepage occurs, some seepage pressure occurs at the top of the bank, pushing the materials down. Because as you saw in that really large bank, it's 200 feet high, but the top of the bank is sitting 300 feet back from the river surface. So there has to be some erosion mechanisms acting at the top of the bank as well at the bottom of the bank. There are some instances along the river where there'll be a straight portions and the bluff is still eroding right next to it, so the meander isn't cutting completely into it. But yes, I mean, for the most part, the bluffs are occurring on the outside of meanders.
Okay, thank you.